Now we're going to dive into our first, what I think is a fun application, which is essentially calculus word problems. So we're going to learn a second type in the next chapter, but the first one we're going to go through is related rates. And so the idea is derivatives are telling us rate of change of some things. You haven't seen necessarily an application. You've seen that it relates what that tangent line slope is going to be. But there's other kind of intuitive stuff that we can use it for. It's giving us the rate of change of one variable with respect to the other. Well, what if this is something that's realistic? Think of time. Time is changing. Things change over time. So if I have someone running, their speed is changing with respect to time. So at every different moment, you're running a different pace. Another example, maybe think of water being pumped into a swimming pool. At that point, you have two quantities that are actually changing. The height of the water is changing, and the volume of the water is changing. They're both increasing, and those rates at which they're increasing are dependent upon each other or related. But if I want to see what that rate is, like how many inches per minute, how many inches per second, I can't do that with the volume so easily. But I could actually measure the rate of increase of the height. Because if I think of just taping a ruler in there, I can see in 60 seconds, it's gone up 1/8 of an inch. I immediately know what my rate of change of the height is. The volume, I can't measure that easily with my eyes. So the idea behind related rates problems is we compute the rate of change of one quantity in terms of another that we can easily measure. So our goal is to find a relation that connects the two quantities. In case of this pool, I know what the volume is based on the height and also the length and width, which don't change. Since both of these quantities are changing with respect to time, we're going to take a derivative with respect to time, which we're going to use the variable t to represent. So let's try an example. The radius of a sphere is increasing at a rate of 4 millimeters per second. Every second, the radius is going to grow by 4 millimeters. We want to figure out how fast is the volume changing, specifically when the radius is 40 millimeters. So in all of these cases, you're going to be given some piece of information and you're going to have some goal. So I always recommend writing this out, whether it's in terms of words or variables. To start, I'm going to do words, and then we'll translate it over to variables. So our given is we're given the rate of increase of the radius. So that's 4 millimeters per second. The goal is we want the rate of increase of volume specifically at the moment when the radius is 40 millimeters. So ultimately, both the volume and radius are changing, so I've got to assign both of them variables. You want to pick stuff that's going to be natural. Don't make volume like A. Try to keep it nice and simple. V, volume, radius, R. So now I can rewrite both of these given and goals in terms of these variables. And their rates, so that means their derivatives. So my rate of increase of my radius is really the rate of change of R with respect to t. So that's dr dt. That rate is 4 millimeters per second. We want the rate of increase of volume, that's dv dt, specifically at the moment when the radius is 40 millimeters. So now I've got to find some equation that connects my volume of a sphere and my radius of a sphere. So I don't anticipate you remember that, but the volume of a sphere with radius r is v equals 4/3 pi times the radius cubed, okay? Now, since both of these are functions of time, we're going to take a derivative with respect to time. So I've got my volume formula, and I want to take the derivative with respect to time. So on the left-hand side, I'm taking the derivative with respect to t. On the right-hand side, we're doing exactly the same thing. and we've got our equal to sign in the middle. So on the left, we're taking the derivative of the volume, which just for simplicity, I'm going to write it's the volume, which is a function of t, so v of t. On the right-hand side, we've got 4/3 pi, the radius, which is also a function of time, cubed. So if I take the derivative of v, I'm getting this rate of change, dv dt. On the right-hand side, the 4/3 pi does nothing, just stays there. Derivative of r cubed would be 3r squared. And then our chain rule tells us I need the rate of change of r with respect to time. So this piece is by chain rule. Just like with implicit differentiation, this variable, the time I'm differentiating with respect to, does not match our variable we're taking a derivative of. So you're getting a v prime and an r prime attached to it. Okay? So this tells us the rate of change of v with respect to time is equal, got some cancellation with these 3's, to 4 pi times the radius squared times the rate of change of r with respect to t. So now, at this moment, we can use that snapshot moment to find dv dt when r is equal to 40. So the rate of change of the volume with respect to time at this precise moment is 4 pi. My radius at this moment is 40 squared. And my rate of change of r is going to be 4 millimeters per second. Okay. So going through all that, 40 squared times 4 would give you 25,600 pi. Now remember, the RDT has units, it's millimeters per second. So my volume is going to have units millimeters cubed per second because it's a volume. So ultimately, the volume is increasing at a rate of 25,600 pi millimeters cubed per second, specifically when the radius is equal to 40 millimeters. You cannot plug 40 at this moment because the volume isn't always equal to that. It is changing because the radius is changing. Okay? So I do have a bit of a problem-solving strategy for you to use here. And we'll do another example though, but you need to get lots and lots and lots and lots of practice with this because you have to be able to, given this information, set up these equations and set up that relationship. So the strategy you want to think of when going through these problems is first, you need to read carefully. There is going to be a lot of information in potentially a very short amount of time. If you can, draw a diagram. Not always going to be able to, like in the last example, diagram didn't help so much. Then you want to introduce notation and assign variables to all quantities that are functions of time. So if that thing is changing, it needs a variable. You might be given numbers, but it is going to represent a snapshot moment. So here, I was given this radius is 40. That is only at one precise time moment. So you cannot say the radius is always 40, which is why it needed a variable in the equation. So be very, 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 very careful with that. So once you've introduced your notation and the variables you want, you're going to be given that information and that goal. You want to express that and the required rate you need to solve for in terms of derivatives and in terms of these variables. Then you're going to need to have some relationship between the quantities. So you want to write some equation that relates all the quantities of the problem. Then you go ahead and differentiate both sides with respect to time, utilizing that chain rule to get that d whatever dt. And then you can use that snapshot moment to plug specific numbers into the equation and solve for the unknown rate. So let's try one last example, which is a good one. We've got a ladder 10 feet long that rests along a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, then how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So you see lots and lots and lots of information going on. So I'm going to jump into drawing a picture. We've got a wall, we've got the ground, we've got a ladder that is resting along this wall. So I'll put some little marks here to indicate that. Okay. You can assume your ladder does make a 90-degree angle. So here's the wall, here's the ground. I've got some unknown quantities. I have some set constants. The ladder is 10 feet long. I can put that this side is always 10 feet because my ladder is not going to change. So this is a fixed number always. Ladder will not grow in size. On the other hand though, this ladder is sliding down, which makes the distance from the wall grow bigger. So ultimately, these two other sides of the triangle are changing. So I need to call one y and one x. We'll keep x to be the horizontal, y to be the vertical. So x is going to be our distance from the wall to the bottom of the ladder. And y is going to be the distance from the ground to the top of the ladder. So now I can go back and kind of utilize these other pieces of information that I'm given. If the bottom of the ladder slides along the wall at a rate of 1 foot per second, that tells me my rate of change of this variable x with respect to time is 1 foot per second. Our goal is to figure out how fast is the bottom of the ladder sliding down, specifically at a snapshot moment. So pretty much what is the rate of change of this height or the distance from the top of the ladder to the ground, okay? So our goal is to find the rate of change of y with respect to t, specifically when the bottom of the ladder is 6 feet. So this distance is not always 6 feet, it is changing, which is why I cannot utilize that 6 yet. That refers to my snapshot moment, okay? So I need to take a derivative with respect to time to be able to get this dy dt. So we need a relationship between these two quantities. Well, it's a triangle, so we can relate x and y using the Pythagorean theorem. So ultimately, my variable x squared plus my variable y squared will always equal 10 squared. So x squared plus y squared will equal 100. Now I'm going to differentiate both sides with respect to time. So I want to take the derivative with respect to time of each piece. And you could write this out if you want to. But the derivative of x squared would be 2x. But chain rule tells you you get a dx dt attached. Derivative of y squared is 2y. And you get the dy dt attached. And then on the right-hand side, derivative of 100 is 0. And ultimately, that's because the length of the ladder is constant, so the length of the ladder will not change. Our goal is to find this quantity, so let's go ahead and solve for dy dt. We'll subtract this to the other side. That gives us 2y times dy dt is equal to negative 2x times dx dt. Then dividing by 2y makes the 2's cancel. The rate of change of y with respect to t is negative x over y times dx dt. So for my goal, I'm specifically looking at when x is equal to 6. I know dx dt. The only unknown on this right-hand side is y. So we know x and dx dt, but before I can find dy dt, I need to see what is y at this particular moment, okay? And I'm just going to utilize the picture. I've got my ladder, and specifically at this moment, the ladder is 10 feet, x is 6. To find y, I'm going to use that Pythagorean theorem that I used at the beginning. So 6 squared plus y squared is equal to 10 squared. So 36 plus y squared is 100. Subtracting 36, 100 minus 36 is 64. Technically, when you take a square root, you get a plus or minus, but we're dealing with a length. So I only have y is equal to 8. So now I have this last missing piece. This tells me at this precise moment, my rate of change of y with respect to time is negative x, which is 6, over y, and dy dt is 1. So this is really negative 3 over 4, and my units are going to be feet per second. So ultimately, the ladder is sliding down at a rate of 3/4 feet per second. So take your time with these. Really don't jump into trying to look stuff up right away, trying to go into the help me solve this. That's only going to really hurt you. You want to sit there and really decipher through everything and draw whatever pictures you need. Figure out that representation on your own.